In this video, we are going to learn about how to calculate percent composition of each element in a compound. First of all, let's define what is percent. Percent is our way out of 100. And what is composition? Composition of a compound is basically the makeup of a compound. And since we are looking for the percent composition of each element, we are looking specifically at each of the elements in the chemical formula that represent a compound. First of all, a pure compound always has a whole number ratios of atoms of different elements. For example, if we look at a chemical formula that represents water, which is H2O, so this is a chemical formula of water molecules. If we look at this chemical formula carefully, you see that there is a whole number ratio of atoms. That is, if we look at the number of hydrogen to the number of oxygen, you would have 2 hydrogen to 1 oxygen. Where if I change this chemical formula to H2O2, notice how this number of atoms is 2 hydrogen to 2 atoms of oxygen. Because of the 2 right here, see how we have nothing here, we have a 2 right there. This substance is called hydrogen peroxide. It has a complete different chemical properties compared to water. In terms of hydrogen oxygen, we would have 2 to 1, and for hydrogen peroxide, we would have 2 to 2. There you go. So these are examples of whole number ratio of atoms of different elements in a compound. If you have a different ratio of atoms, you can tell right away it is a complete different compound. Also, a ratio can be expressed in terms of mole. For example, I can say we have 2 moles of hydrogen to 1 moles of oxygen, or 2 moles of hydrogen for hydrogen peroxide to 2 moles of oxygen. Or we can just express in atoms. Again, we mentioned atoms before up here. We can have 2 atoms of hydrogen to 1 atoms of oxygen. Or over here, we have 2 atoms of hydrogen to 2 atoms of oxygen. Or we can express them in ions, okay? We have ions in this case. If they were exist in terms of ions, you would have an ions form, but these are covalent compound and they don't make any ions. Now, let's just say if I have another compound and make ions. So we have calcium hydroxide. And we know this is forming from the calcium 2+ and the OH-. In this case, how many OH- do we have? We have 2 of the OH- right there, but for calcium, we only have 1 calcium. So we can say that the calcium ions to the hydroxide ions is 1 to 2. And most importantly is that the ratio can be expressed in terms of mass or the percentage by mass. Now this is a completely different world of itself. That is because different atoms have different atomic mass based on the periodic table. So you cannot just relate it directly based on the subscript in a chemical formula. We have to convert mole to mass before we can express them as a ratio of mass or percentage by mass. And here we have again, this sentence just basically saying that the ratio in mass is not the same as the ratio in atoms or moles or ions. Because again, different elements have different atomic masses. We have something as simple as H2O. If we look at in terms of moles or atoms, we would have 2 atoms of hydrogen to 1 atoms of oxygen, or 2 moles of hydrogen to 1 moles of oxygen. But if we look in terms of mass and we use our periodic table, the mass for hydrogen is 1.01, okay? And the mass for oxygen is 16.0. So we have 2 times 1.01 equal to 1 times 16.00. And we have our overall ratio in mass is 2.02 to 16.00. And this ratio is not equal to the number ratio in terms of moles or atoms. And that is the difference between a ratio in mass versus a ratio in moles, atoms, or ions. However, one of the most beautiful things about percentage is that Since we are talking about a pure samples, so we have a sample of a pure substance, so therefore it consists of the same substance. If we have a cup of pure water, it's going to be a bunch of pure water by itself, which is H2O. So all we have to do is look at only one compound. In this case, I have this sample right here. Let's assume that this sample is a cup of water that weighs 10 grams of H2O, okay? But here's the most important part, is that all we have to do is look at the properties or the structure of one compound and find the percentage of each element in this compound, and that percentage can apply to the entire sample. So why is that so important? But first, let's look at the formula to find percentage by mass of an element in a chemical formula. That is, percentage by mass of an element is equal to the total mass of that specific element in a compound, which makes sense, okay? And that is divided by the total mass of all the elements in the compound. And basically, this is right here is your molar mass of that chemical formula. Let's look at this sample more specifically. For instance, let's say I want to find percent by mass for hydrogen. And for hydrogen, in this case, if we look at one compound, which is H2O, it has how many hydrogen? It has 2 hydrogen, so we would say 2 times the number of hydrogen. This is the mass from your PT. And then down on the bottom, we would have the molar mass of water. In this case, if we look at H2O, we have hydrogen. There are 2 of it. 2 times 1.01 equal to 2.02. And for oxygen, it's 1 times 16.00, and that gives us 16.00. And we add them together, give us our molar mass, 18.02. So here we would have the chemical formula for H2O, and 2 times 1.01, that is our molar mass for hydrogen, or the atomic mass of hydrogen on the periodic table, divided by the molar mass for water. In this case, it's right here, which is equal to 18.02. And if we use a calculator and we calculate it, give us 0.112. And of course, this is relative to 1. If we want to convert to a percentage, we have to multiply by 100. And now that will be relative to 100 for percentage, which gives us 11.2%. So in a chemical formula for water, we would have 11.2% of hydrogen. And this, of course, is by mass. So how is that important? If we look at the example together as a whole, this sample is 10 grams of water. By using the application of percentage, we can take this relative to 1, times the entire sample, and that gives us the mass of hydrogen in this 10-gram sample. For example, we take 10.0 times 0.112, give us 1.12 gram of hydrogen in that sample. Now, and also percentage is out of 100 again, right? And we look at this chemical, there are only 2 elements, and if I find the percentage by mass for hydrogen, I can also find the percentage by mass for oxygen as well. So all I have to do is take 100% minus 11.2%. That will give us 88.8%. And if we look into a relative of 1, we take 1 minus 0.112, and that's, of course, give us 0.888. And this represents oxygen. So let's do some example problem. Calculate the percent composition of each element in 3 moles of magnesium hydroxide. And again, look at the 3 moles. Do we care about the 3 at all? Remember the previous problem, if we have the entire sample of the same substance, all we have to do is look at 1 mole or 1 compound. So we can just ignore the 3 when we calculate our percentage composition for each of the elements in the compound. So let's look at the first one that we have. And again, here is the formula to find percent by mass of an element. The total mass of an element in a compound over the total mass of all the elements in the compound. And we are only looking for one compound, okay? So keep that in mind. So for the percentage for magnesium, of course, if we look at the compound, notice I don't have the 3 because we only need to focus on 1 mole. So in magnesium hydroxide, I have only 1 mg. And then, of course, over the compound. And the mass for magnesium is, on the periodic table, 24.31. But how do we figure out the mass of magnesium hydroxide? Of course, we had to calculate the molar mass for magnesium hydroxide. And here again, I have 3 moles of magnesium hydroxide, but we don't really care about the 3. And we're only looking for one compound. Magnesium, we have 1. Oxygen, we have 2, because this distributed inside the parenthesis. And hydrogen, we have 2. And here I have the molar mass for magnesium, and I have the molar mass for oxygen, and of course the molar mass for hydrogen on the periodic table. And I multiply them across. This gives us a total mass of magnesium in magnesium hydroxide. And 2 times 16 give us 32, give us the total mass of oxygen in this compound. And 2 times 1.01 give us a total mass of hydrogen in this compound. And we add them all up, give us 58.33 grams, equal to 1 mole of magnesium hydroxide. And again, this is your molar mass. So that's how we have 58.3. And we use a calculator to solve for it, which give us 0.417, or we convert to percentage by multiplying 100, 41.7%. Another thing, and we do the same thing to oxygen, except for now, the mass is going to be the mass of oxygen. Notice I have 2 oxygen, so 2 times 16 over the same mass of the compound, because we are working with the same compound. And we plug this into the calculator, give us 0.549, or in percentage, we have 54.9. Then we go to the last one, which is hydrogen. Since we are looking for hydrogen, again, the mass is going to be relative to hydrogen, which is, in this case, we have 2 hydrogen in the compound. 2 times 1.01, that's the mass from the periodic table. And in this case, it's again divided by 58.33 because we are working with the same compound. So what we have here is 0.0346, or in terms of percentage, it is 3.46%. And if we add all the percentages together, guess what's going to happen? It's going to equal to about 100. In this case, it's equal to 100.06, which is very close to 100%. And if we look at the relative number of 1, if we add them all together, that would give us 1.006, which is very close to 1. See how relative number is 1, in this case, percentage is out of 100. And that's how we calculate percent composition for each element in a compound.